Welcome back to the deep dive. It feels like just yesterday we were truly blown away by what large language models could accomplish.
It really does. The pace is just incredible.
But the landscape of AI shifts incredibly fast, doesn't it? And we're already witnessing, well, a profound evolution, a move from AI that's essentially fixed after training.
Right, static models.
Exactly, to systems that can genuinely improve themselves continuously. It's like observing a complex machine, not just operating flawlessly, but actually figuring out how to reconfigure its own gears and circuits to run even better moment by moment.
That's a powerful analogy
Yeah.
and very apt. We are, without a doubt, on the cusp of a new era.
So what are we diving into today?
Today, we're taking a deep dive into what many are calling the next frontier in AI, self-evolving agents.
Self-evolving agents, okay.
This concept builds directly on the incredible capabilities of current large language models,
Yeah.
but it propels them into an entirely new dimension of adaptability, autonomy, and continuous growth.
And we've got some solid grounding for this exploration, right?
We do. Our guide is a truly comprehensive survey paper from arcs4v.org, identified as document 25007.21046.
Ah, okay, good. A deep survey paper.
It's an insightful roadmap, really charting the progression of these self-evolving systems.
So what's our mission for this deep dive then? What are we hoping to unpack?
Our mission is to unpack the core technical details and the significant implications of these agents. We'll explore precisely how they learn, adapt, and, grow over time.
And as always, on the deep dive, we're keeping the focus tight, right?
Exactly. Our focus will be purely on the mechanics of this technology and its astonishing potential. We'll be steering clear of the ethical or inclusivity considerations.
Which are definitely important topics.
Hugely important, but just beyond the scope of this particular technical deep dive. Our goal is to give you, the listener, a structured, clear understanding of this complex and rapidly evolving field.
Okay, sounds good. And we've laid out a clear path for our discussion today.
We have. We're going to start by defining exactly what these self-evolving agents are. Then we'll dive into what specific aspects of their intelligence can actually evolve.
What can change, basically.
Right. After that, we'll tackle when this evolution takes place. Is it always on the fly, or do they learn retrospectively?
Interesting timing question.
Then we'll unravel the how, the various methods and algorithms that drive this continuous change.
Mechanisms.
Exactly.
Yeah.
We'll also look at where these agents are already being applied, both generally and in specialized fields.
Real-world impact.
And finally, we'll discuss how researchers technically evaluate their progress, which, as you can imagine, is a unique challenge when the system itself is a moving target.
Right, evaluating something that's constantly changing. That sounds tricky.
It is. So it's a journey from the very core concepts right through to their real-world impact and future trajectory.
Okay, let's unpack this. We've all interacted with, or at least heard of, the incredible capabilities of large language models like OpenAI's GPT-4 or DeepSeek R1. They can generate text, answer questions, even write code with astounding fluency.
They're truly remarkable tools.
But the paper we're reviewing points out a crucial limitation. These models are fundamentally static. What does that mean in practical terms, and why does the static nature create a bottleneck for their capabilities, especially in, a dynamic world?
That's a critical distinction, yeah. And it goes right to the heart of why self-evolving agents are such a significant leap.
Okay.
When we describe current LLMs as static, we mean that once they are trained and deployed, their internal parameters, that vast network of weights and biases defining their knowledge and reasoning, are fixed. They simply cannot alter or adapt those core parameters in real time.
So no learning on the job, essentially.
Not at that fundamental level. Think of it like this. A highly trained expert who has absorbed an enormous amount of knowledge. They can retrieve information, they can reason with what they know. But if they encounter a truly novel situation, something entirely outside their training data, they can't genuinely update their core understanding or learn new fundamental skills on the fly.
Ah, I see. They can only apply what they already possess.
Precisely.
So if these systems are interacting in an open-ended environment, one where the situation is constantly changing, their inability to fundamentally adapt their internal structure becomes a huge roadblock. They can't truly learn and evolve from the live feedback they're getting.
Exactly. That limitation creates a critical bottleneck, especially in truly open-ended or highly interactive settings. Think about navigating the internet or controlling a robot in an unpredictable physical space.
Or even just a long, evolving conversation.
Right. If the environment or the task shifts in an unexpected way, A static LLM might just falter because its internal rules or knowledge aren't flexible enough to incorporate that new real-time information.
Okay.
And this recognition directly leads to the necessity for agents that can dynamically adapt their perception, refine their reasoning processes, and modify their actions in real time.
So it marks a fundamental conceptual shift.
It really does, moving beyond simply scaling up static models to developing self-evolving agents.
So it's not just about building a bigger brain, like you said, but building a brain that can continually rewire itself based on new experiences. That's a huge conceptual leap forward.
It is a really profound shift.
And the paper even talks about this concept leading us down a path towards artificial superintelligence, or ASI. What does that conceptual trajectory look like? Is that the ultimate goal here?
Well, the paper positions ASI as the hypothetical culmination of this trend, yeah.
Yeah.
In this conceptual future, agents wouldn't just learn and evolve from experience.
Uh-huh.
They would do so at an unpredictable and accelerating speed. They'd perform at or above human-level intelligence across an incredibly wide array of tasks.
Becoming general purpose intelligences.
Effectively, yes, continuously improving themselves through autonomous learning and adaptation. The paper actually illustrates this trajectory in Figure 1, moving from foundational LLMs to more capable foundation agents that can use tools and plan, then to these self-evolving agents we're discussing today, and finally, conceptually, to this idea of ASI.
And the key differentiator is that continuous autonomous learning.
That's the core idea. The exciting promise of this field is this constant autonomous learning and adaptation. It allows these systems to become inherently more robust, versatile, and capable of tackling incredibly complex, dynamic, real-world problems that static models just couldn't handle.
That makes a lot of sense. It's like the difference between, I don't know, a highly specialized calculator and a human brain that can learn completely new skills, new languages, even new ways of thinking throughout its entire life.
That's a good way to put it.
And the paper gets quite specific, laying out the groundwork for what an agent system formally is. It's a bit technical, I know, but I think it's important for understanding the underlying mechanics. Can you walk us through the core components that make up these self-evolving agents from this formal perspective, maybe in a way that helps us truly grasp their function?
Absolutely. And you're right, the formal framework is essential for really digging into the mechanisms.
Yeah.
To start, we need to consider the environment where these agents operate.
Right, their world.
Exactly. This includes everything the agent interacts with. Could be a user giving a query, could be a complex software environment like a Linux shell, anything.
Okay.
This environment is formally conceptualized as a partially observable Markov decision process, or POMDP.
Partially observable Markov decision process. That's quite a mouthful. What does that mean for how the agent perceives and interacts with its world? Is the partially observable part the key?
It is a key part, yes. Essentially, it means the environment is dynamic. The agent has goals, it can take actions, it observes consequences, it gets feedback. Standard stuff for agents. But partially observable means the agent doesn't necessarily have a complete full picture of everything happening in the environment at all times. It only sees what its sensors or observations allow it to.
So it has to make decisions based on incomplete information.
Precisely. Which mirrors many real-world scenarios, right?
Yep. Yeah.
The formal definition, the double SATRAAA, breaks this down. You've got G, the set of potential goals, S, the environment states, A, the possible actions.
Actions like reasoning, getting knowledge, using tools.
Exactly. Textual reasoning, external knowledge retrieval, tool calls. Then T is how states change. R is the feedback or reward.
And that feedback can be just a score or actual text.
It can be either a scalar score or more nuanced textual feedback. Then AE is the set of observations it can access, and O is the probability of seeing a certain observation. And A is a discount factor, common in these models.
Okay, so the environment is complex, dynamic, and the agent has limited sensory input.
Got it. Now, what about the agent system itself? What are its fundamental building blocks according to the paper?
Right, the agent system, AAAXCI, whether it's a single agent or a group, is defined by its core components.
Okay, let's break those down. First is the architecture. Think of it like the agent's internal blueprint. It determines the control flow, how information is processed, how decisions are made, or how different parts of a multi-agent system might collaborate.
Like the org chart or the flow chart.
Exactly. Then represents the underlying large language models or multimodal models. These are the actual brains of each part or node of the agent. The cognitive engine's doing the heavy lifting.
Makes sense.
Then C is the context information. This is vital. For any part of the agent powered by an LLM, this includes the specific prompt, PI, or instruction it's given, and its memory, storing relevant past info. This context really shapes the LLM's immediate behavior.
The prompt and memory.
Crucial, absolutely.
Yeah.
And finally, we is the set of available tools or APIs. These are the external functions the agent can call, like a human using a calculator or searching the web.
Okay, architecture, LLMs, context tools.
So given a task and its observations from the environment, the agent's policy at each node, guided by its architecture and powered by its LLMs, where Klein includes the model A and context A, decides what action A to take next.
And those actions can be language or tool calls?
Yes, the action space includes both natural language generation and the tool space. After taking an action, it gets feedback, or either externally or internally.
This sounds incredibly intricate, all these interacting parts. So what actually drives the self-evolving part? How does this whole system actually improve itself over time? Where does the evolution happen?
That's where the self-evolving strategy comes in. It's essentially a transformation function.
A transformation.
Yeah, this function takes the agent system in its current state, looks at the sequence of actions and observations, the trajectory it generated during a task, and processes the feedback it received. Based on all of that, it maps the current agent system to a new, updated, and ideally improved agent system. So ASHO R. After completing a task and getting feedback, the agent modifies itself in a structured way.
And this modification isn't just random, right? It's guided.
Exactly. It's guided by an objective function for evolution. This is a utility function, UPday, that measures the agent system's performance on a task, T, usually resulting in a score.
So it's trying to maximize that score.
Precisely. This utility can be derived from the task feedback or combine things like completion time, accuracy, robustness. The key is that this self-evolving strategy recurrently generates a sequence of agent systems. ACHA plus 1, DOTARAA.
So each version learns from the last one's experience on a task.
Correct. With each new task or iteration, the agent system evolves, learning from that trajectory and feedback, continuously optimizing towards that defined utility function. It's a closed loop of continuous improvement, driven by its own experiences.
Okay, this is where it gets really interesting for me. We understand what these agents are now, these complex, dynamic systems that learn. The next huge question is, what exactly can they evolve? What parts of themselves can change? The paper breaks this down into 4 key pillars, right? Showing that almost every aspect can potentially adapt.
Indeed. These 4 pillars represent the fundamental dimensions along which a self-evolving agent can adapt and improve. They are its core models, its context, its tools, and its overall architecture.
Let's start with the cognitive core then, the models.
Right. At the most fundamental level, model evolution means agents can continuously update the parameters of their underlying large language models or multimodal large language models based on their own experiences and interactions.
So agents can continuously update the fundamental parameters governing their reasoning and behavior through their own experiences. Are we talking about the agent literally fine-tuning its base LLM on the fly? Or is it something more subtle than full retraining?
It can involve both, although, full-scale retraining of a giant LLM on the fly is usually computationally prohibitive in real-time scenarios.
Right, that would be intense.
But it definitely means adapting the model's internal cognitive core. Some methods allow the agent to learn directly from its experiences and feedback to refine its policy, how it makes decisions.
Can you give an example?
Sure. Think about approaches like SCA, self-rewarding, self-improving models, or RAGEN mentioned in the paper. These might involve the model acting as its own reward function, generating data to refine itself, or using reinforcement learning to continuously update reasoning capabilities in interactive settings.
So it adapts its decision-making over time.
Exactly.
Yeah.
The goal is to create a truly adaptive cognitive engine that genuinely gets smarter and more efficient through its lived experience, not just staying static after initial training.
Okay, that's powerful. That leads perfectly into the next pillar. Context. I imagine this is a huge one, since context is so central to how LLMs operate. How does context shape agent behavior? And maybe more importantly, how can that context itself be evolved?
Context is absolutely vital, yeah. It directly shapes the LLM agent's immediate behavior. The paper highlights 2 main ways context evolves, through memory evolution and prompt optimization.
Memory and prompts. Okay. Are they completely separate?
They're related because both affect what's in the context window, but they have distinct focuses. Prompt optimization is about how we phrase instructions to get better behavior. Memory evolution is about how we intelligently store, manage, and retrieve past information over longer interactions.
Got it. So let's start with memory evolution. How do these agents accumulate knowledge and skills over time? Is it more than just a simple log file?
Oh, much more. Memory evolution is about designing agents with dynamic long-term memory mechanisms that grow and adapt.
Grow and adapt.
How?
Well, it's not just logging. It's a sophisticated system for accumulating knowledge, recalling relevant past events, and adjusting behavior based on that cumulative experience. Some systems, for instance, use concepts inspired by human memory, like the Ebbinghaus forgetting curve.
To decide what to forget. Exactly. To optimize relevance and avoid overload. Others, like Men0, might use a two-phase pipeline. Extract key facts, then decide whether to ADD, merge update, or delete information in the long-term memory.
So it actively manages its knowledge base. Systems like MemInsight, adding semantic structure, or remember using RL signals.
Precisely. Those are great examples from the paper. But a truly crucial aspect here isn't just retrieving exact past instances. It's about learning general heuristics or skills from past experiences, distilling them into broader guidance.
So not just I did X when Y happened, but more like when a problem like Y comes up, strategy Z usually works well.
You got it. Examples like Expel generating insights and rules from trajectories, or agent workflow memory recording reusable subtask sequences, or even the Richelieu diplomacy agent refining negotiation strategies via self-play.
Ah, learning from simulations.
Right. These approaches transform one-time experiences into long-term competencies. It shows how memory evolution is a cornerstone, allowing agents to accumulate wisdom, not just data.
Wisdom, not just data. I like that. Okay, what about prompt optimization? This sounds like it's more about refining the instructions the agent receives rather than its internal memory store.
Precisely. Prompt optimization, PO, lets agents self-evolve by refining the actual instructions, the prompts, they feed to their own backbone LLM. This directly alters the model's behavior without needing to modify its fundamental pre-trained weights.
So it changes behavior without changing the core model. How does that work?
Early research treated it like a search problem. Methods like APE or RPO would generate lots of candidate prompts and pick the best one.
Okay, brute force-ish.
Kind of. But more advanced techniques have emerged. Pertigi generates natural language corrections to edit the prompt, almost like textual gradient descent. Prompt Agent uses Monte Carlo tree search to explore the prompt space strategically. Prompt Breeder uses evolutionary approaches.
Evolutionary prompts, that's cool.
It is. And what's really remarkable is SPO self-prompting optimization, which creates a fully self-contained loop. The model generates its own training data and refines its prompts based on its own pairwise preference comparisons. No external labels needed.
Wow, completely autonomous prompt improvement.
It's a potential game changer.
Mm-hmm.
And this isn't just for single prompts, it extends to complex multi-node systems.
Like entire workflows.
Exactly. Frameworks like DSPy treat the whole workflow as a graph, jointly tuning subprompts. Trace, TextGrad, LLM AutoDiff even treat prompts like parameters in differentiable programs, propagating natural language gradients through the process.
Language gradients. Fascinating concept, and for multiple agents.
Yeah, for multi-agent systems, prompt optimization focuses on tuning individual role prompts and the communication between agents. MARIS-S optimizes role prompts and inter-agent messages. MAS0 dynamically proposes and revises roles. Evo Agent, Agent Square use evolutionary methods to find specialized teams.
So it's evolving the instructions for whole teams of AIs.
Right. It's about evolving the very language that defines entire workflows or even societies of interconnected agents.
Okay, that's incredibly powerful. This idea of a system constantly rewriting its own operating manual. Now, the third pillar, tools. We know LLMs can use tools called a search engine, a calculator, but the paper talks about them becoming autonomous tool makers. How significant is that transition?
It's a truly significant transition.
Yeah.
A fundamental shift, moving agents from being just tool users stuck with a fixed set to becoming autonomous tool makers.
So they can create their own capabilities.
Exactly. It lets them dynamically adapt their capabilities to solve complex problems their designers never even envisioned. The motivation is clear. Overcome the limits of a fixed tool set, gain flexibility, innovate on demand.
How do they actually do that? Make tools?
The methodologies cover a spectrum. At one end, you've got opportunistic discovery. Think of Voyager and Minecraft. It builds a skill library through emergent trial and error driven by exploration.
Learning by doing, basically.
Pretty much. Then there are more reactive approaches. Systems like Alita or ATS use RGAC to search open source code or even write new functions when they hit a capability gap.
Writing code on the fly.
Right. On the more structured end, Creator disentangles the abstract idea of creating a tool from using it, for better modularity. SkillWeaver analyzes human or agent actions to synthesize reusable APIs. And Crafty focuses on specialized tool sets for expert performance in specific domains.
So a range from spontaneous to engineered tool creation.
Exactly. Though, it's important to note this autonomy in code generation brings safety and security challenges. Researchers are actively working on verification and sandboxing for that.
Naturally. And once a tool is created, it's probably not perfect right away, right? So how do they achieve mastery? Is it just using it a lot?
Not just use, it's absolutely about iterative refinement. A new tool is often brittle, inefficient, so you need robust self-correction loops.
Learning from mistakes with the tool.
Precisely. Systems like LearnAct or DAFTA learn from their own experience using the tool. This involves tackling the tricky credit assignment problem.
Figuring what went wrong in the code.
Exactly. Which line of code, which parameter caused the failure. They analyze feedback signals, compiler errors, API returns, changes in the environment, even implicit user actions.
Okay.
And the goal isn't just debugging the code, it's also refining the documentation doc strings, argument descriptions.
Why the documentation?
So the agent itself can understand and use the tool better next time. It's a continuous honing process, taking a maybe error-prone skill and making it reliable, improving the quality, not just quantity, of its skill library.
That's like an AI-driven agile development cycle for its own tools.
Very cool. Yeah. Okay, final pillar, architecture. This seems like a meta-level evolution. The agent optimizing its own internal design, its blueprint. How does that work? You're right, this is a really fundamental shift. The agent treats its internal logic and collaborative structures as optimizable components. It moves beyond fixed designs. And it happens at both single-agent and multi-agent levels.
Okay, let's start with single agents. How do they optimize their own structure?
We see two main strategies. First, LLM invoking node optimization. This is about refining individual parts within a fixed overall architecture.
Tweaking the components, not the whole structure.
Right. TextGrad, for instance, uses those textual gradients we mentioned to propagate feedback and refine nodes without changing the overall structure. The second strategy integrates this into a broader architecture search. Here, node characteristics become tunable parameters in a bigger search space. EvoFlow uses evolutionary algorithms to pick the best LLMs for each task in a workflow, or frameworks might embed prompt engineering into the search.
Finding the best workflow and instructions together.
Exactly. Then there's a more profound level, autonomous agent optimization. Here, the agent is treated holistically, capable of modifying its high-level design. Agent Square uses evolutionary algorithms to find optimal combinations of modular components, planners, memory modules, etc. Even more radically, some research explores agents modifying their own source code.
Like the Darwin-Gödel machine.
Precisely. Recursively modifying its own Python code, balancing performance and novelty. AlphaVolve uses evolutionary coding to improve algorithms it uses. Gödel agent has a self-referential framework. The vision is agents analyzing and altering their own fundamental logic.
The blueprint itself becomes learnable, mind-bending.
It really is.
Okay, what about multi-agent system optimization? How do groups of agents co-evolve their structures and interactions to become a better team?
This focuses on how multiple agents co-evolve internal policies through interaction, leading to emerging capabilities like coordination, delegation, collective problem-solving. Two main lenses here, agentic workflow optimization and multi-autonomous agent optimization.
Okay, agentic workflow optimization first. What's that about?
This generally focuses on finding the most effective, often static, structure for communication and task delegation in a team. Early work, automated linear workflows. Later, graph-based frameworks like GPT-Swarm emerged. A breakthrough came with formalizing this as a search optimization problem, like in ADAS or AFlow, using things like Monte Carlo tree search to navigate the huge design space. And these automatically discovered workflows can sometimes outperform human designs.
Better than human-designed teams.
Wow. In certain tasks, yeah. Research has diversified into search-based methods like Moss's SuperNet and learning-based methods, ScoreFlow, FlowReasoner training models to generate topologies. The big challenge is the computational cost of evaluating each potential workflow.
Trying out every possible team structure sounds expensive.
It is. So researchers are developing lightweight prediction models, like the agentic predictor, to estimate performance without full execution, speeding things up significantly.
Clever workaround.
Sure.
Okay, what's the other lens?
Yeah.
Multi-autonomous agent optimization.
Right. This is distinct from explicit workflow design. It focuses on how multiple autonomous agents co-evolve their internal behavior policies through continuous interaction, leading to emergent group capabilities.
So the agents themselves learn to cooperate better.
Exactly. Multi-agent reinforcement learning, RRL is used, for example, in REMA to train systems with distinct roles, like a high-level metathinker and low-level executors.
Yeah.
GitGPO enhances MAROL by aggregating trajectories for better credit assignment in complex coordination tasks. And open-source infrastructure like Marty is helping scale these experiments.
So ROL is key here.
It's a very promising route for cultivating sophisticated group-level skills that individual agents couldn't achieve alone. It's about agents learning to be better team players and leaders, not just better individuals.
Okay, so agents can evolve pretty much every aspect of themselves. Models, context, tools, even architecture. That's a massive scope for adaptation. But when does this evolution actually happen? You mentioned this earlier. The paper draws a distinction between immediate, in-the-moment adaptation and more retrospective learning. This timing seems really critical.
You're absolutely right. The temporal dimension is crucial. We categorize the timing into two main modes: intra-test-time self-evolution and inter-test-time self-evolution. This basically highlights when the self-evolving strategy gets invoked and applied.
Okay, intra-test time first. What does that mean?
Inter-test-time self-evolution refers to adaptive processes that happen during the actual execution of a task.
While it's working on the problem.
Exactly. Imagine the agent hits a snag or recognizes a limitation on that very problem. It immediately kicks off targeted learning mechanisms to boost its capabilities right then and there in real time.
So it's synchronous with the task.
Tightly coupled, yeah. The agent is literally improving its ability to solve that specific problem as it encounters it. It creates this dynamic interplay between performance and adaptation.
How does it do that in real time? What are the mechanisms?
It often leverages three fundamental learning paradigms, all applied in real time. In context learning, ICL, supervised fine-tuning, SFT, and reinforcement learning, RL.
So during the task, not afterwards. What's the practical implication of learning during a task versus between tasks? And can you give us some examples of how these paradigms play out in real time?
The big practical implication is immediate responsiveness, overcoming unexpected hurdles right away. For in-context learning, ICL, during intra-test time, agents mostly use their context window as a dynamic, short-term memory, immediate adaptation without changing core model parameters.
How does that work? Self-reflection.
Exactly. They employ self-reflective mechanisms, analyzing their own performance on the current task, maybe generating verbal critiques of their actions.
Like reflection or self.
Right. Storing these reflections in episodic memory to guide the next steps within the same task. Learning from their own recent mistakes on that specific attempt.
And revising plans.
Yes, systems like AdaPlanner can dynamically revise their plan based on real-time feedback. They can even distinguish if feedback fits the current plan or suggests a whole new approach, adapting strategy on the fly for safety or efficiency, like Trust Agent, all without permanent model changes.
Okay, what about real-time supervised fine-tuning? That sounds like it does change the model.
It does, but often in a lightweight way. SFT for immediate self-modification is a paradigm shift where models perform actual self-modification through learned meta-adaptation strategies.
Meta-adaptation?
Yeah, imagine a model encounters a tough sub-problem.
Yeah.
It might generate self-edits, meta-level instructions guiding it on how to restructure info or use tools better for this task. These self-edits then trigger immediate lightweight fine-tuning, persistent weight updates, but adapted specifically to the current task or problem type. The real innovation is meta-learning, training models to produce effective self-edits, teaching models how to teach themselves in real time for immediate benefit.
Wow, learning how to learn on the fly and real-time reinforcement learning.
RL for on-demand skill acquisition. This lets models develop entirely new capabilities right when they need them for problems beyond their current competence.
Like learning a new skill just in time.
Exactly. Ladder demonstrates this with test-time reinforcement learning, TTRL. If it hits a problem it can't solve, it doesn't just quit.
What does it do?
It can generate focused, simpler versions of that problem and run intensive, targeted RLs specifically for that problem class. It turns roadblocks into immediate learning opportunities. Just-in-time skill acquisition during deployment, solving problems that would otherwise be out of reach.
That's incredibly powerful, learning and adapting in the heat of the moment, like an athlete making real-time adjustments mid-game. Okay, let's shift to the other side. Inter-test-time self-evolution. How does that differ, and why is it important for long-term growth?
Inter-test-time self-evolution happens between task completions. It's fundamentally retrospective.
Looking back at past performance.
Right. Leveraging accumulated experiences from many past tasks to improve future performance. Learning algorithms operate on historical data curated datasets or logs of past trajectories.
So it decouples learning from immediate task solving.
Exactly. It decouples task performance from capability improvement. This allows agents to consolidate experiences, spot broad patterns of success and failure, and systematically refine their policies without the real-time compute constraints of active task solving. It's all about long-term growth and strategic refinement.
Okay, how do those same paradigms, ICL, SFT, RL, work in this retrospective mode? Let's start with in-context learning.
For ICL in this inter-test-time mode, agents use results and feedback from previous tasks as rich context for future problems. Wang et al. Showed how an agent can induce effective workflows from past action histories and store them for later use.
Reusing successful patterns.
Right, and there's in-context reinforcement learning, ICRL, where agents maintain extensive histories in their context window. The idea is that pre-trained networks can implicitly do RL just by processing this accumulated context, adapting behavior without explicit updates. The key is progressive improvement as task-relevant info accumulates over many experiences.
Okay, and retrospective supervised fine-tuning. How does that work without real-time feedback?
SFT here often involves iterative self-improvement through synthetic data generation and self-evaluation.
Generating its own training data.
Yeah. Systems like self first acquire metacognitive abilities, self-feedback, refinement. Then they iteratively generate responses to unlabeled instructions and enhance them through self-critique, creating their own high-quality training data.
Like star and quiet star improving reasoning through rationalization.
Exactly. They attempt problems, and if they fail initially but later get it right, they generate explanations for the correct answer. This creates augmented training data, targeting reasoning chains. Sirius extends this to sequential problems, maintaining repositories of correct solutions and refining past failures.
So models bootstrap their own improvement by evaluating and enhancing their outputs. Less need for human supervision.
Precisely. Generating high-quality training signals from imperfect attempts.
And finally, retrospective reinforcement learning. How does that differ from the real-time version?
RL in inter-test time leverages unconstrained computational resources, usually in a pre-deployment or offline phase. This allows for extensive environmental interaction and sophisticated curriculum design.
More time, more data.
Right. Systems like Ragen and Distal use online RL for multi-turn interactions, continuously refining policies over extended periods. Others use cognitive-inspired training with adaptive difficulty problems get harder as the agent gets better.
Like learning. Like humans.
Yes. And domain-specific applications are really exciting here. WebRL uses self-evolving curricula for web navigation, dynamically adjusting task complexity. DeGirl trains device control agents via autonomous RL, mastering real-world interactions through potentially thousands of attempts that would be impractical in real time.
So this allows for much deeper, broader learning through extensive trial and error.
Exactly, developing robust, generalized policies over time.
Okay, this raises a really important question for me. We've covered what evolves: models, context, tools, architecture, and when it evolves intra-test time or inter-test time. Now let's get into the how. What are the actual methods, the algorithms, the underlying mechanisms that drive this continuous improvement?
Good question. The paper systematically maps out the major families of self-evolution methods. It focuses on how they actually implement that evolving strategy, F, that transforms the current agent into the improved one.
Right, the transformation function.
We can look at three main families of these mechanisms: reward-based, self-evolution, imitation and demonstration learning, and population-based and evolutionary methods. And then we'll touch on some cross-cutting dimensions too.
Okay, let's start with reward-based self-evolution. This sounds like it's all about feedback.
It is. It centers entirely on the crucial role of feedback, specifically the design of reward signals to guide that iterative self-improvement. How that feedback is structured and delivered is critical for the nature, efficiency, and effectiveness of the learning.
So it's about getting the right kind of feedback to tell the agent if it's doing well or poorly. What are the different ways they provide this feedback? Is it just a simple good job or bad job?
Oh, it's much more nuanced than that. We can categorize these reward signals into four main types. First, textual feedback.
Using language itself as feedback.
Exactly. Leveraging the LLM's native modality. Natural language provides highly detailed, interpretable instructions. Unlike just a number score, text offers nuanced critiques, actionable suggestions. It's incredibly rich for an LLM.
Examples, like reflections verbal reinforcement learning.
Precisely. Storing reflections as episodic memory. Or ADA Planner using feedback for plan revision. self-refine, and using iterative self-feedback for improvement without external data. It highlights the power of language as a flexible, sample-efficient reward channel.
Okay, language feedback. What's next?
Second, internal rewards. These exploit the model's own intrinsic metrics.
Like its confidence.
Exactly. Using its own probability estimates or certainty scores to guide improvement without needing external supervision. CISC weights reasoning paths by confidence. Self-ensemble mitigates confidence distortion. And the really groundbreaking ones are the self-rewarding language models.
Where the model is its own reward function.
Yeah, generating training data through self-instruction and self-evaluation cycles. These dramatically reduce reliance on human labels, enabling truly scalable, autonomous self-improvement loops.
Fascinating. Okay, third type.
Third, external rewards, derived from sources outside the model itself.
Like the environment. Or rules.
Right, could be feedback from the environment, consensus from multiple model outputs, majority voting like in self-train LM, MMUPT, COVO, or explicit rules.
Environment feedback seems central for agents.
It absolutely is.
Yeah.
SWEDEV, SICA, feedback friction, UE's agent, still, they all use signals from tools or the environment. Rule-based rewards using explicit constraints are great for structured domains like math, OTCPO, autorule, ladder, region, spiral, or gameplay. These signals are objective, often reliable, but might need significant setup engineering.
Makes sense. And the last type of reward.
Finally, there are implicit rewards. This is based on the intriguing idea that LLMs can learn from feedback signals even when they aren't explicitly labeled as rewards.
How does that work?
Some research, like reward is enough, suggests LLMs perform in-context RL using simple scalar signals just embedded in the context, no explicit RL fine-tuning needed. Others propose that standard next token prediction implicitly teaches a generalist reward function hidden in the model's logits. And frameworks like PIT implicitly learn improvement goals directly from human preference data without defining good or bad reward explicitly.
So discovering reward signals that are just inherent in the language modeling process itself.
Exactly. It's a fascinating area. Suggested reward might be more fundamental than we thought.
Okay, that covers reward-based evolution thoroughly. What's the second major mechanism the paper outlines?
The second is imitation and demonstration learning. Here, agents improve by actively reproducing and refining successful behavioral patterns.
Learning by example.
Essentially, yes.
Oh.
Often through iterative self-training and bootstrapping, where the agent generates its own examples or learns from others. It's highly effective when you have good demonstrations or the agent can make them itself.
Okay, how does that break down?
3 types. First, self-generated demonstration learning. Agents create their own training data via refinement.
Like the STAR framework.
Exactly. STAR is foundational here, generating reasoning chains, fine-tuning on correct solutions, repeating the cycle. VSTAR adds a verifier. AdaSTAR uses adaptive sampling. This also extends to multimodal self-training vision language models, training on their own image descriptions, Yihei Deng et al., or GenXer using multimodal LLMs as data generators.
So they teach themselves using their own successful attempts. What's the second type?
Second, cross-agent demonstration learning. Learning from demos provided by other agents, internal or external.
Learning from peers.
Right. Sirius uses a shared experience library of successful interaction trajectories for knowledge sharing in multi-agent systems. In specific domains like recommenders, Softice shows LLM-based systems learning from successful recommendation patterns of others.
Okay, and a third?
Hybrid demonstration learning. Combines self-generated and external demos for more robust, diverse training.
Best of both worlds.
Kind of. RISE has agents introspect on their reasoning, find weaknesses, then generate corrective demos. IOE uses the model's uncertainty to select high-quality demos, filtering out bad examples. The key here is the quality and diversity of demonstrations. It can be a challenge if good examples are scarce. The goal is maximizing the learning signal from all available examples.
Got it. Learning from examples, self-made or otherwise. What's the third major family of self-evolution methods?
The third paradigm is population-based and evolutionary methods. This draws deep inspiration from biology and collective intelligence.
Survival of the fittest, for AIs.
In a way, yes. Instead of just one agent learning, you maintain multiple agent variants simultaneously. This allows parallel exploration of strategies and the emergence of diverse capabilities through selection, mutation, crossover, competition.
When is this particularly useful?
It's valuable for exploring complex solution spaces, or when you need fundamental architectural changes, as it allows a broad search for optimal designs.
Okay, how does this apply to single agents versus groups?
For single-agent evolution, 2 main approaches. First, Learning from evolution. The Darwin-Gödel machine, DGM, is a fascinating example. Open-ended evolution, recursively modifying its own Python code, balancing performance and novelty. Genome uses genetic algorithms directly on LM parameters, crossover, mutation, selection on model weights.
Evolving the code or the weights themselves.
Right. The second approach is self-play for multiple rollouts. Agents improve via iterative self-competition. Spin has current models compete against previous versions, creating evolutionary pressure. SBC uses adversarial coevolution, a sneaky generator versus a step critic.
Yeah.
STL uses self-teaching evolution via look-ahead search, generating training data from its own rollouts, all leveraging the agent's own generated experiences.
Competing against past selves or adversaries. Cool. What about multi-agent evolution?
For multi-agent evolution, the focus shifts to evolving entire teams or networks. This includes system architecture evolution. EvoMac mimics neural network training from multi-agent systems using textual backpropagation with feedback like compile errors to modify team composition and prompts. Puppeteer uses the central orchestrator that evolves its policy for selecting agents, balancing performance and cost.
Evolving the team structure or the manager.
Exactly. Then there's knowledge-based evolution. This emphasizes evolving collective knowledge through memory accumulation and case-based learning, often via in-context learning. MD Team GPT uses dual knowledge bases for successes and failures. MedAgentSim applies this to medical simulations, agents accumulating experience from patient interactions to improve diagnostics collectively.
So evolving the shared knowledge of the team.
Right. Leveraging collective experience.
Okay, that covers the main mechanisms. But the paper also mentions some cross-cutting evolutionary dimensions that offer a more nuanced view. Can you elaborate on those? They seem to connect the when and how.
Yes, these add crucial layers. First, online versus offline learning.
We touched on this with the when.
We did. Online learning is continuous adaptation with live interaction. Voyager exploring Minecraft. Ada planner refining plans mid-task. Diggerel training directly in the wild. Offline learning uses pre-collected data or historical trajectories. Self-train LM, star, quiet star, improving from self-generated data between tasks. More controlled, extensive training cycles.
Okay, what's the next dimension?
Second, on-policy versus off-policy learning. This relates to whether agents learn from experiences generated by their current policy, on policy, or by different policies, off policy.
What's the trade-off?
On policy, like reflection, GRPO, DAPO, offers high stability behavior, doesn't change wildly. But it can be sample inefficient, needs fresh data from the current agent version. Off policy, learning from past versions preferences like Rafailov et al., or using ranking supervision like RRHF or experience libraries like Sirius, offers high sample efficiency by reusing old data. But it faces challenges with distribution shift. The old data might not match the current agent, potentially causing instability.
Stability versus efficiency. Got it. And the third dimension?
The third, reward granularity, the level of detail in the feedback. Outcome-based rewards evaluate the final result, success or failure. Used in DPO, RRHF, rejection sampling in AutoWebGLM, Diggerel WebRL. Simple, but learning from complex failures can be hard.
Just knowing you failed doesn't always help you figure out why.
Exactly. Process-based rewards offer precise, granular feedback at each step. Process-supervised reward models, PRMs, are often more reliable than outcome-based ones, or RMs, in complex reasoning like math. Examples include Math Shepherd, Affimath, or StarMath, Agent PRM, but they traditionally need lots of human annotation.
Which is expensive.
Right. Hybrid rewards combine both, clarity of outcome plus granular guidance. YGPO and CPARL use dual-level rewards, distributing outcome-based reward across intermediate steps, providing both high-level goals and low-level corrections. These distinctions are vital for understanding how feedback actually drives evolution.
All right, now that we've thoroughly explored the inner workings, the what, when, and how of self-evolving agents, let's look at their practical impact. Where are these sophisticated systems actually being put to work today? The paper highlights both general and specialized domains, right?
Indeed. The applications are vast and rapidly expanding, showing their versatility and transformative potential. Broadly, we can group them into two categories.
For sure.
General domain evolution, where agents enhance capabilities across a wide variety of tasks, often becoming versatile digital assistants. And specialized domain evolution, where they deepen expertise and achieve high proficiency within narrower, often critical task sets.
Okay, let's start with the general domain, versatile digital assistants that get better over time.
Exactly. These agents aim to become truly adaptable helpers across a broad spectrum of digital tasks. They achieve this mainly through two key mechanisms we've discussed. First, sophisticated memory mechanisms.
Using memory for broad adaptability.
Right. Agents summarize historical successes and failures into refined memory representations. Anticipating these distilled experiences will help with new unseen tasks. Mobile Agent E uses tips, general guidelines, and shortcuts, reusable action sequences, for complex smartphone tasks. Mobile Steward coordinates multiple app-specific agents and uses memory-based self-evolution, summarizing successful cross-app executions to improve overall performance. The concept of generative agents also fits here, storing and retrieving diverse memories for broad adaptability in conversations.
And the second mechanism for general agents.
Curriculum-driven training. This is key for building these general-purpose self-evolving assistants. The agent autonomously develops a sequence of learning tasks, like a human learning step-by-step.
The agent creates its own syllabus.
Pretty much. WebRL uses a self-evolving curriculum for web navigation.
Okay.
It generates manageable subtasks upon failure, leading to better success rates. Voyager in Minecraft uses an automatic, bottom-up curriculum. GPT-4 proposes tasks based on current progress, building a skill library through iterative prompting and feedback.
So agents autonomously expand their capabilities through iterative task adaptation across diverse scenarios.
Exactly. Powerfully illustrating how they can become generally more competent over time.
That's a powerful vision for a truly adaptable digital assistant. But then there's the specialized domain evolution. This sounds like aiming for deep expertise in specific, often complex areas. Where are these agents making a significant mark?
In specialized domains, yes, the evolution is precisely tailored to significantly boost proficiency within narrower task sets. Let's look at some key areas.
Okay.
First, coding. Self-evolving agents are actively transforming software engineering. Sika is a self-improving coding agent that edits its own code base, improving performance on benchmarks.
Wow, editing its own code.
Yeah. EvoMac introduces self-evolving multi-agent collaboration networks, optimizing prompts and workflows for code generation, outperforming manual designs. Agent Coder uses a multi-agent framework programmer, tester, test designer, working together for iterative refinement.
Like a mini software team of AIs.
Exactly. And Zhang et al. Showed agents evolving by filtering high-quality answers, stratifying experiences by difficulty, and adaptively selecting demos, even constructing ML libraries. These advances dramatically enhance coding efficiency and quality, moving towards truly autonomous software engineering.
Okay, coding is a big one. What else?
Next, graphical user interfaces, GUI, extending LLM capabilities from text to directly manipulating desktops, web, mobile interfaces. This is tough. Large action spaces, different layouts, partial visual info.
Yeah, GUIs are messy.
They are. You want it all. Couple pixel-level vision with self-reinforcement to refine click accuracy without human labels. The Navi agent for Windows replays and critiques its failures, doubling task completion rates. Web Voyager fuses screenshots with reflection and self-fine-tuning for unseen sites.
Adapting to new websites on the fly.
Right. ReAP adds episodic memories for failed queries. AutoGA continuously mines functionality annotations from interfaces to expand its skill library. Mobile use uses a hierarchical self-reflection stack for smartphone actions. These systems embody the full triad of self-evolution: what, when, how, pushing towards universally competent interface agents.
Impressive progress in a challenging area. What about finance?
In the financial domain, they're tackling a major bottleneck: building vast, accurate, domain-specific knowledge bases. Quant Agent uses a two-layer framework to iteratively refine responses and enhance its knowledge base using simulated and real-world feedback for trading tasks.
Learning from market feedback.
Yes, improving predictive accuracy and signal quality. Trading Agents incorporates dynamic processes like reflection, RL, real-world feedback, and even collaborative debates among agents to refine trading strategies. This underscores the potential to revolutionize finance by autonomously building expertise, adapting to markets, and improving decision-making.
Okay, finance. What about education?
Education is seeing strong applications for personalized learning and instruction. PACE is a personalized conversational tutor that adjusts prompts based on student profiles and refines questioning strategies. It even uses LLM to LLM self-play to fine-tune itself.
AI tutors learning from simulated students.
Right. MathVC simulates a multi-character virtual classroom with a meta-planner orchestrating problem-solving. AVP uses a team of cooperating LLM agents: coach, assessor, feedback generator, critiquing each other, adapting explanations, evolving via expert feedback for professional development.
A team teaching approach by AIs.
Yeah. AdaPlanner frames lesson plan creation as an adversarial loop reviewed by evaluator optimizer agents. Sayfield uses teacher-student self-play to generate homework feedback examples, fine-tuning a lightweight feedback model to improve comment quality for students. These examples show how self-evolving agents can dynamically adapt to both learners and instructors, driving more personalized, effective, and scalable education.
Okay, if we connect this all back to the bigger picture, given how these agents are constantly changing, learning, improving, adapting their very core, traditional ways of evaluating AI just don't seem like they'd cut it anymore, right? How do researchers assess truly self-evolving systems, where the target is always moving and the system itself is transforming? This sounds like a really unique challenge.
It absolutely is a crucial point, and yes, it presents a unique set of challenges. Evaluating these agents effectively requires a fundamental shift.
Because they're designed to continuously learn and adapt.
Exactly, through ongoing interaction with dynamic environments. Traditional single-shot assessments test a model once on a fixed dataset are inherently insufficient for this.
Right, that only gives you a snapshot in time.
Precisely. We need methods that capture adaptivity over time, knowledge retention across tasks, long-term generalization to new scenarios, skill transfer, all while mitigating catastrophic forgetting.
Where learning new stuff makes it forget old stuff.
Right. This demands moving from conventional single-shot tests to a more longitudinal view of their growth trajectory.
Okay, so how do they structure this evaluation? What are the goals?
To get a holistic view, the paper categorizes key evaluation goals into 5 core dimensions, nicely summarized in their Table 5.
5 dimensions. Okay, let's break those down. What's the first?
First is adaptivity. This measures the agent's ability to improve performance on tasks within its domain as it gets more experience. It's about tracking how performance improves over time, steps, or iterations.
Not just if it succeeds, but how much better it gets.
Exactly. Metrics include success rate by iteration steps, tracking performance versus interaction history, and adaptation speed, how quickly an agent hits a performance threshold or converges. This tells us how effectively it's learning in the moment.
Okay, adaptivity, dimension 2.
Second, retention. Crucial for evaluating knowledge-based stability and mitigating catastrophic forgetting. We need to know if learning new things erodes old knowledge.
How do they measure that?
2 key metrics: forgetting, FGT, and backward transfer, BWT. FGT measures the average accuracy drop on old tasks. After learning a new one, are we losing useful experience? BWT measures the average accuracy improvement on old tasks from new experience. Positive BWT means successful knowledge transfer, a more integrated learning process.
Ah, interesting. So learning new things can actually help with old things sometimes.
Ideally, yes.
Hmm.
That's positive backward transfer.
Okay, third dimension.
Third is generalization. While adaptivity and retention focus on in-domain performance, generalization measures if the agent can apply accumulated knowledge to new unseen domains or tasks.
Cross-domain performance. Can it take what it learned here and apply it over there?
Precisely. Metrics include aggregate performance, means success rates across multi-domain test suites like Agent Bench, and out-of-domain performance, using held-out task distributions to simulate truly novel scenarios.
Got it. Fourth dimension.
Fourth, efficiency. Quantifying resourcefulness, cost, speed of the evolution process. Vital for practical use.
How much compute, how much time?
Exactly. Key indicators: token consumption, compute cost, time expenditure duration, number of steps, actions to reach goal, and tool productivity. Benefit versus cost of using tools like an OTCPO. Lower values generally mean more efficient operation.
Makes sense. And the final dimension, you said 5.
And finally, safety. This critically examines if these agents develop unsafe or undesirable behaviors during their continuous evolution. It assesses adherence to rules and propensity for harmful actions.
Super important as they become more autonomous. What are the metrics?
Several. Safety score measures adherence to predefined safety criteria. Harm score uses a grading rubric for harmful outputs. Completion under policy checks if a task is done while strictly following rules. Risk ratio calculates rule violation frequency. Refusal rate assesses how often agents decline unsafe requests. And leakage rate tracks unintentional leaks of sensitive info. These are vital for ensuring agents evolve within acceptable boundaries.
Okay. Adaptivity, retention, generalization, efficiency, and safety. A truly multidimensional assessment. Now, what about the actual paradigms for evaluation? How do researchers structure these tests temporally, given the dynamic nature?
The evaluation paradigm categorizes assessment based on its temporal scope: static, short horizon, and long horizon.
Okay, static first. That sounds like traditional evaluation.
It is. Static assessment evaluates instantaneous performance at a specific point in time. crucial for baselines or after discrete training phases. It includes external task-solving evaluation for end-to-end proficiency on benchmarks like Science Agent Bench, SWE Bench, OSWorld, Web Arena, and internal agent components evaluation for core competencies, Plan Bench, Tool Bench, LTM Benchmark, Multi-Agent Bench. Typical metrics, accuracy, success rate, F1 score. A snapshot, but doesn't capture the continuous learning.
Right. So short horizon.
Short horizon adaptive assessment goes beyond static. It assesses adaptation and improvement over a short period or limited interactions like multiple attempts on the same task instance. Captures immediate adaptability.
How do they do that?
Researchers can augment traditional benchmarks by tracking performance over iteration steps, like ADS, AWM, WebEvolve are used. Some benchmarks have built-in dynamic evaluation designed for short-term dynamic learning, like Memory Agent Bench's test time learning dimension. Metrics here are success rate by iteration steps, learning curve analysis, adaptation speed, good for initial learning, but limited view of long-term effects.
Which brings us to long horizon. This sounds like the real test for self-evolving agents.
It is. Long horizon lifelong learning ability assessment is crucial, yet nascent. It focuses on the agent's ability to continuously acquire, retain, and reuse knowledge across diverse environments over extended periods.
What are the big challenges here?
Significant ones. Catastrophic forgetting, robust knowledge transfer across different tasks, efficient resource management over long times, and mitigating data leakage when evaluating continuously on evolving data distributions.
Evaluating on data that's also changing? Tricky.
Very. Emerging benchmarks, that LTM benchmark, focus on long-term memory with conversational tests and distractions. Lifelong Agent Bench uses sequences of interdependent tasks requiring progressive skill building. Dynamic benchmarks are also being developed, like benchmark self-evolving, to update datasets and alleviate leakage. Metrics here include forgetting FGT, backward transfer BWT, cost per gain, and long-term generalization on evolving OAT tasks. This area is a key frontier for truly evaluating the promise of lifelong learning agents.
So after diving deep into what self-evolving agents are, how they learn, where they're being applied, and how we even evaluate them, what does the future hold? The paper doesn't just look back. It points to critical open challenges and promising research directions too, right? What's on the horizon for these dynamic systems?
Absolutely. The path forward is both incredibly exciting and, filled with significant technical hurdles. The paper highlights 3 crucial areas that will likely define their future development.
Which are?
Personalizing AI agents, achieving robust generalization, and developing effective ecosystems of multi-agents.
Okay, let's take those one by one. Personalizing AI agents. What's the goal there and what are the hurdles?
The goal is for agents to accurately capture and adapt to individual users' unique patterns and preferences over long interactions. Think truly personalized chatbots or digital twins that perfectly mirror your workflow.
Like a human assistant who really learns your habits.
Exactly. But the challenges are significant. Current personalized agents often rely heavily on lots of labeled data, which is hard to get. There's the cold start problem. How do agents build up understanding with limited initial data?
Right, starting from scratch with each user.
And enabling personalized planning and execution requires really effective long-term memory, smooth tool integration, and making sure generated content consistently aligns with the user's facts, preferences, and evolving needs. Plus, we need better evaluation metrics for personalization, as static ones don't capture the evolving dynamics well.
Makes sense. Personalization is key for adoption, but definitely sounds complex and data hungry. What about generalization? You mentioned a fundamental tension there.
Yes, generalization remains one of the most pressing challenges. The fundamental tension is between specialization, being great at one thing, and broad adaptability, being good at many things. Agents optimized for specific tasks often struggle to transfer skills to new environments without lots of retraining.
So how does this play out?
In scalable architecture design, there's that trade-off. Specialized architectures might not be flexible, and the compute cost of dynamic reasoning grows fast with complexity, limiting broad generalization within practical resources. Reflective and memory-augmented capabilities have smaller models, but still face limits in complex, sustained adaptation scenarios.
Okay. And cross-domain adaptation.
Cross-domain adaptation is critical. Current methods often need domain-specific fine-tuning, limiting adaptability. Taking a tech support agent and making it work in healthcare isn't easy. Promising paths involve test time scaling, inference time adaptation, meta-learning for rapid adaptation. But knowing when to allocate extra resources and doing it efficiently is key.
Right. What about forgetting things?
That's continual learning and catastrophic forgetting. Agents need to adapt continuously while retaining old knowledge. LLMs are prone to forgetting. It's the stability-plasticity dilemma: be flexible but stable. Retraining entirely is too costly.
So what's the solution?
Research is exploring parameter-efficient fine-tuning, selective memory mechanisms, incremental learning strategies. But finding the optimal balance between efficiency and preventing model drift, especially with limited resources or streaming data, is still a major open challenge.
And transferring knowledge between agents.
Knowledge transferability also has limitations. Studies show agents often fail to effectively propagate new knowledge from individual interactions to others in a group. This restricts collaborative potential. It suggests they might rely on shallow pattern matching, not robust, transferable world models. Future work needs to understand reliable knowledge generalization, measure transfer limits, and encourage robust world model formation for better collaboration.
It sounds like true adaptability hinges on becoming genuine generalists, not just specialized learners. Okay, final direction. Multi-agent ecosystems. What are the unique challenges when multiple self-evolving agents interact?
Developing ecosystems of multi-agents faces several unique issues. One is balancing individual and collective reasoning.
The lone genius versus the wisdom of the crowd.
Kind of. Studies show it's hard to balance independent thought with effective group decision-making. Group discussion helps, but agents can become overly reliant on consensus, stifling individual critical thinking or innovation.
So groupthink, but for AIs.
Potentially. Future work needs dynamic mechanisms to adjust the weight of individual versus group input, promoting balanced consensus and innovation. Explicit knowledge bases and standardized update methods could also help agents evolve better and contribute more effectively individually within the group.
Okay. What else for multi-agent systems?
Another crucial challenge is developing efficient frameworks and dynamic evaluation. There's a gap identified. No clear mechanisms for agents to dynamically manage and update shared knowledge bases. We need new frameworks integrating continuous learning and adaptive collaboration across the system.
And evaluation is tricky again.
Yes. Existing multi-agent benchmarks are mostly static. They don't capture the long-term adaptation of roles or team dynamics. Future benchmarks need truly dynamic assessment methods, reflecting ongoing adaptation, evolving interactions, and diverse agent contributions. We need better metrics for these evolving ecosystems.
It's definitely clear we're just at the beginning of understanding the full implications and, frankly, the technical complexities of these self-evolving agents.
Absolutely. The journey from static LLMs to these truly dynamic adaptive intelligences is profound, and the research outlined in this paper provides an excellent technical map of where the field currently stands and where it needs to go.
And as we wrap up this deep dive, maybe a final provocative thought for you, our listeners. If self-evolving agents can continuously learn and adapt without human intervention, maybe even improve their own designs, what does this imply for the speed and nature of technological progress itself in the coming years?
That's a big question.
How might this fundamentally reshape our approach to problem solving in dynamic environments, perhaps even in your own field, as these systems become more autonomous in their learning and evolution?
It's a question that really challenges our current notions of innovation and development, doesn't it? It pushes the boundaries of what we thought possible with AI.
Indeed. We encourage you to mull over these implications. Think about how these concepts might apply to the dynamic challenges you encounter. For more insights into the latest AI and machine learning research, remember you can always visit our webpage, linked in the bio. Thank you for joining us on this deep dive into self-evolving agents.
So until next time.